calculus, fun without limits.
Alright, so class, today we're going to be talking about derivatives, but what we really need to go over first are tangent lines. See that thing right there? That's a tangent line. It's a line that touches a curve at a single point. Alright, so now that we've covered tangent lines, let's go over what a slope is. The slope is obtained by the change in the y over the change in the x, which is essentially the definition of a derivative. So here, let's take this graph for example. This point is 1, 2, and this one down here is -1, -2. So in order to get the slope, we're going to have to take the y of this one minus the y of this one over top of the x of this one minus the x of this one. So let's write that out. So we get 2 minus the -2 over 1 minus the -1. Which is 4 over 2, which is equal to 2. Alright, so now we're going to talk a little bit about the mean value theorem. And here's what it states. So, the derivative of some value at c of the original function is equal to f of one value minus f of the other value over the two x values subtracted from each other. Alright, so what this really is stating is that the average value of the function over some interval we're finding the point where the instantaneous is going to be equal to that. Alright, so now we're going to address differentials. And a differential is a derivative with the dx that got moved over. So if we were to take a derivative of this function, we would get dy dx equals f prime of x. So that's just a simple derivative of a function. So all we're going to do to make it a differential is move this dx over by multiplying it. And that would also set it up for an easy integration. If you just apply the integral symbol out in front, you would get back y equals f of x. So an extension of differentials are linearizations, which you change this dy into a delta y, and you say a y value minus a given y value equals m times the x value, just an x, minus a given x value, where the m is your dy dx, evaluated at some xy value. So now there are three rules that a function must follow for us to be able to take a derivative. The first one value at c of the function f of x must exist. The second one, the limit as x approaches c of f of x must exist. And the third, links the first two together and says the limit as x approaches c of f of x must equal f of c. Alright, so now we're going to look at some examples of differentiable functions. Here we have a polynomial that would resemble some even function, say x squared. You can see that it exists on the entire domain, and on the entire domain it has a limit. So we can take a derivative at any point for this function. For trig, we have something that resembles sine, and really the same thing. It exists for all domain x, and you can take a tangent here, here, because the limit will equal the value. And same for exponential, something like e to the x. It will go all the way up to infinity really fast, but you can still be taking tangent lines over the whole domain. So now we're going to look at some examples graphically and function-wise at non-differentiable functions. So here we have an example of a corner, which can be given by absolute value of x. As you can see at the bottom, it comes down to a corner. So we can draw a tangent line to that, which, we learned earlier, going to touch it at one point, but we can draw an infinite number, so it's not really a tangent line. For cups, an example would be x to the 2/3, and that'll look like this, and it's pretty much the same thing as a corner, just a corner will have linear lines coming together, and a cusp has some kind of parametric. And then for removable and infinite, we combined the two and we came up with a piecewise function. So you can look at this for any value x is less than or equal to 2. You have this little part right here. So 1 is going to negative infinity on this side, and on the other side it's going to positive infinity. So you are not able to take a derivative here because the limit does not exist. And same over here. With the removable, x is greater than 2 on this side, so it's going to go up like that. So since we have two different values, the limit doesn't exist, and that makes it a non-differentiable function.
Rules that need to be accounted for. Today we'll be talking about some of these rules. We will discuss product rule, chain rule, quotient rule, and how to take derivatives with constants. Let's first cover the basic rules of derivatives. So our first rule here is the constant rule. And what the constant rule says is that when you're taking a derivative of a constant, which is any real number, you will get 0. So on to our next rule here, we have the constant multiple rule. And that states that when you take the derivative of a constant times a function, you will get the constant multiplied by the derivative of the function. So let's look at an example here. If we had 3x squared, and you were taking a derivative of this function, your 3 would act as your constant and your x squared would act as your function. So that would mean that when taking the derivative, it would be 3 times the derivative of x squared, which is 2x. So in the end, you will have 6x as your final answer. Now these are the basic rules of derivatives, and these will allow you to move on to more complicated. So the next topic that we want to discuss is quotient rule. And quotient rule is the derivative of f of x over g of x, which comes out to be g of x times f prime of x minus f of x times g prime of x all over g of x squared. So basically what we're doing here is we're taking the bottom, multiplying by the derivative of the top, minus the top multiplied by the derivative of the bottom, all over the bottom squared. So, for example, if we had x squared over x plus 3, and you were taking a derivative of this function, you would treat the top here, x squared, as your f of x, and the bottom, x plus 3, as your g of x. When taking your derivative, you're going to want to keep the bottom constant, multiply the top x squared by its derivative, which is 2x, subtract that by the top, keeping it constant, multiply by the derivative of the bottom, x plus 3, so that would be 1, all over the bottom squared. And there you have it, that's your quotient rule.
Today we're going to be talking about the product rule. So the product rule is defined as d dx f of x times g of x equals f prime x, hold the g of x, and then add f of x and take the prime of g of x. So for example, you have the function 2x times x plus 1. To take the derivative, let's first call this f of x. So it matches our rule times g of x. Okay, so 2f prime is 2 times x plus 1, and then we're going to add 2x times 1. So then we have 2x plus 2 plus 2x, which equals 4x plus 2. Following the product rule, we have the extended product. So with the extended product, we have three functions. We have f of x, g of x, and h of x. So when we take the derivative, we're going to get f prime of x, g of x, h of x, plus f of x, g prime of x, h of x, plus f of x, g of x, h prime of x. So what we're doing is we're taking the derivative of each one, in the first part, we're taking the derivative of the first one, holding the other two. Here, we're taking the derivative of the middle one, holding the other two. And then here, we're taking the derivative of the last one, holding the other two. So if we have 4x times x plus 1 times x squared plus 2x as our function, this we will call f of x, this g of x, and this h of x. So when we take the derivative, what we're going to get is, first we're going to derive the first one, so we're going to have 4x plus 1 and x squared plus 2x. And then we're going to have hold. This will be a 1 when you derive it. And then x squared plus 2x. And then for the last one, we're going to hold the 4x and hold the x plus 1, and then derive this, which will be 2x plus 2. And that is the extended product. The next derivative rule we're going to talk about is the chain rule. For the chain rule, you have a function f of g of x. You're going to take the derivative of it, and you're going to get f prime of g of x times g prime of x. You can think about it as the derivative of the outside, hold the inside, and then multiply it by the derivative of the inside. So for example, if we have 3 times 3x cubed plus 1, quantity squared, is our function. We're going to call this f, and we're calling this g of x. So then when we take the derivative, we're going to have 3, we're going to pull the 2 out, multiply it by 3, so we're going to have 6 times g of x is constant, 3x cubed plus 1. And then now, the inside, we're going to take the derivative, so it's going to be 9x squared. And that's chain rule.
Let's digress into the 6 trig deriv rules. Taking a derivative of a trig function requires a long proof, so it is advised you memorize the following derivatives to complete problems more efficiently. The derivative of sine x equals cosine x. The derivative of cosine x equals negative sine x. The derivative of tangent x equals secant squared x. The derivative of cotangent x equals negative cosecant squared x. The derivative of secant x equals secant x times tangent x. And the derivative of cosecant x equals negative cosecant x times cotangent x. Now, a little helpful reminder is that all of the cos are going to result in a negative derivative.
Okay, let's move on to the derivatives of log and exponential functions. So just like trig functions, these should be memorized. So we have the derivative of e to the x, which is nice because it's e to the x. And then this is the derivative of a to the x. It's different from e to the x because this is just any constant other than e. So we have the derivative of a to the x is a to the x times the natural log of a. And then for the natural log of x, when you take the derivative, it's just 1 over x. And then for the derivative of log b of x, it's 1 over b ln of x. Now that we just learned how to derive trig functions, we're going to apply the chain rule. As you may recall, the chain rule involves deriving an outside function, keeping its inside constant, and then taking the derivative of the inside. So first, our first example, we're going to call sine f, and then this g of x. Okay, so first you take the derivative of f, so our derivative of sine is cosine. And then this stays the same, and then we multiply by the derivative of g of x, which is 2x. So we're going to have 2x cosine of x squared. Our next example, we have cosecant as f, and then 3x plus 1 is g of x. When you derive cosecant, you're going to get negative cosecant 3x plus 1 times cotangent 3x plus 1, and then times the derivative of the inside, 3. So then you're just going to have negative 3 cosecant 3x plus 1 cotangent 3x plus 1. And that is the chain rule with trigs.
Let's look at some examples of chain rule with logs and exponentials. Let's begin with e to the u, which is my personal favorite. So, the derivative of e to the u, as we discussed earlier, is e to the u, but we have chain rule present here. So we're going to have to take the derivative of u as well and multiply it by e to the u. So let's look at this example right here. We have the derivative of e to the 3x. So our 3x is going to serve as u. So the first thing you want to do is you want to write out the original problem, which is e to the 3x, and then you want to take the chain rule of the u, which is your 3x. So the derivative of 3x is 3. So your final answer for this problem would be 3e to the 3x. Moving right along, we now have the derivative of ln u. So we know that the derivative of ln u is 1 over u, but we have to take the chain rule of u. So it becomes 1 over u times du dx. So looking at this example right here, we have ln of x to the 6th. So we're first going to look at x to the 6th as our u. So 1 over x to the 6th. And now we want to take the derivative of our u. So that would become 6x to the 5th. So our final answer for this problem is 6x to the 5th over x to the 6th. Now, for the derivative of a to the u, we're going to have a to the u times ln of a times du dx, which again is the chain rule portion. So for this example right here, we have 2 to the x squared. So first what we want to do to take the derivative is have our a to the u, which is the original 2x squared, times the ln of a, which is ln of 2. And now for our chain rule part, the x squared, which we call our u right here, which would be 2x. And that would be your answer. And last but not least, we have log base b of u. So the derivative of this would be 1 over b to the ln of u times du dx. Looking at another example, we would have our 4 would serve as b, and our 7x cubed would serve as u. So first what we want to do here is 1 over b, which is 4, times the ln of our u, 7x cubed. And now for the chain rule portion, taking the derivative of 7x cubed, which becomes 21x squared. And that would be your answer.